Hey everyone, Patrick Kennedy here from Microchip. In this video, I'll cover the ins and outs of differential input analog to digital converters. First, we'll put them in context relative to a traditional single-ended ADC, which will later shed insight into how differential ADCs can be used to improve sensor resolution and reject common mode noise. As a quick side note, I'm only going to cover the concepts in theory further detailed in this white paper. I personally keep it as a reference, so I'd highly recommend checking it out afterwards. If you're more interested in how this looks in practice, feel free to check out the next video linked on screen and in the description that highlights how to set this up from scratch on the AVR-DA microcontroller variant of the Curiosity Nano development platform using Start and Studio. I've also included some other links to code examples, tutorials, and app notes if you want to see implementation details and advanced use cases. Okay, so some of you watching this probably already know, ADCs convert continuous analog signals to discrete digital representations. They are one of the basic building blocks that enable a digital circuit to react to real-world or analog events like user input devices or sensors. Now, the performance of an ADC is primarily characterized by its bandwidth, which represents the quantity of data that can be captured or handled at any given moment, and the signal-to-noise ratio, or SNR, which represents the quality of that data. While the bandwidth is primarily determined by the sampling rate, the SNR is a bit more complex and is related to things like resolution, jitter, and common mode noise. Luckily, this is precisely where differential ADCs can help, primarily by improving ADC conversion or sensor resolution, and by rejecting common mode noise, both of which will improve the signal-to-noise ratio. Now, a traditional single-ended ADC will output a result proportional to the voltage on a single input pin relative to a voltage reference and ground. For a 12-bit single-ended ADC, this means the maximum output value will represent any input voltage above the voltage reference. Similarly, any input voltage below ground will read 0. Utilizing a 3-volt voltage reference means that those 12 bits of resolution are spread across the 3-volt range. In other words, our 4096 distinct values equates to a resolution of approximately 0.73 millivolts. However, what happens if our application only requires us to sample voltages between 2 to 3 volts? Perhaps we need to interface with a sensor that produces an output in that range, or maybe it includes some degree of DC offset in its reading. In this case, the effective resolution of our 12-bit ADC will be much lower. In single-ended mode, we are only afforded roughly 1400 values over that range, which would be more like using a 10-bit ADC. A differential input ADC will solve this by generating an output proportional to the difference of the two inputs, allowing us to effectively focus in on the voltage range we are interested in without sacrificing resolution. This is accomplished by setting the negative input equal to the midpoint of the expected input voltage range. The result will be a signed integer around a midpoint of the negative reference voltage. This means that a reading of 0 will correspond to the negative reference voltage. For a 12-bit conversion, the maximum value will correspond to the sum of the negative input pin and the ADC voltage reference value. The same is true for the lowest value. This means our effective resolution is approximately 0.24 millivolts, which gives us our original 12 bits. For the AVR-DA microcontroller, you can further use the on-chip digital-to-analog converter as the negative input to the ADC, and an external voltage reference as the ADC reference voltage so that you can use all available bits for that voltage range. Additionally, the positive and negative inputs can be sourced internally from other on-device modules like the DAC, while the ADC reference voltage can similarly be sourced from the power supply, a dedicated on-device voltage reference module, or an external pin for the sake of flexibility. If you're interested in how that looks in practice, check out the next video that highlights how to set this up from scratch on the AVR-DA microcontroller. You'll notice there are a bunch of other features on the ADC of this device, like configurable thresholds, window comparison, and accumulation. While those features are cool, I'm only going to focus on the differential feature for today. However, if you're feeling adventurous, I left links in the description below to a variety of code examples, tutorials, and application notes that detail their usage. Okay, so now that we have covered how to improve our ADC resolution, which will boost our measured signal, how can we improve SNR by reducing the noise? Well, going back to our single-ended ADC, we can see the addition of some noise only further degrades the quality of the signal. It's important to note that noise in general can come in two main forms. First, noise along the signal path can come from power lines, RF signals, and other switching frequencies. And second, noise on the microcontroller ground and reference voltage levels, which is known as common mode noise. In the first case, twisting or routing the positive and negative inputs together will affect both signals equally, and will just be cancelled out by the differential input. In the second case, the reference voltage levels and microcontroller ground will be equal and will similarly cancel out. If you want to see how you could actually set this up on a device, check out the links in the description to videos, tutorials, source code, and other documentation. Remember to leave your thoughts in the comments below, or like and subscribe so you can get updates for new videos showing you how to build and optimize your next embedded design. Thanks for watching.